Welcome back, and let us continue with the next lecture on energy conservation and waste heat recovery. If you recall, in the last class we started with energy storage, and as part of energy storage techniques we started with mechanical energy storage. We had an introduction to the first type of mechanical energy storage, which is pumped hydro storage. We looked at this schematic. As we saw that pumped hydro storage, what happens is we have two reservoirs at elevated level. So, one is at the lower level and the other reservoir is at a higher level, maybe at the top of a cliff. Okay. So, what happens is during off peak hours, let us say during night time, when the demand is low and the supply is higher than what I require, then the additional electricity which is generated is used to run a pump which is going to pump the liquid up, or in this case water, up from the lower reservoir to the upper reservoir. So, by this means what happens? The water gains potential energy. So, this is the energy that is released, let us say during the daytime when the load is higher than supply, or the demand is higher than supply. Then this water from the upper reservoir flows down and hits the turbine. As we recall, the type of turbine is the Francis type of turbine that is used, that can function both as a pump for pumping it up as well as a turbine. So, that when the water comes down and hits the Francis turbine and makes it rotate, we get additional electricity. So, this is an example, or this in a nutshell is how the pumped hydro storage works. Okay. So, now what happens? This is also a picture that we drew last time as to how a pumped hydro storage, the schematic. So, let us do some analysis now. So, if I say that the height over here, or the head that the water attains is h. Okay. So, therefore, the potential energy that we get, or that is stored, is mgh. So, this is the energy stored. Clear? However, what is the pumping head required? This is going to be H plus, I would say, HL, where HL are the pumping, or let me say HP. HP is a pumping head loss. Clear? So, this is when you are in the pump mode. In the turbine mode, what happens? The turbine will also have some loss. There is nothing like a perfectly efficient or 100% efficient turbine. So, turbine head will be H T is also going, or turbine head is also going to be H minus H T. All right. And what is H T? Is a turbine head loss. So, therefore, if you look at it, what is the turnaround efficiency? The turnaround efficiency is going to be mg h minus ht over mg h plus hp. Clear? Okay. Now, keep in mind, however, in this case, or for example, for that matter, let me just write it down. Efficiency will be energy recovered over energy spent, okay, and none of these are necessarily equal to energy stored. Energy recovered will normally be less than energy stored, and energy spent will normally be more than energy stored, right. All right. So, now let us say what is the amount of work energy that we can store? It is huge. Okay. So, the quantities of energy that we can store in pumped hydro systems is very large, okay. 1000 megawatts or even larger. That is a lot of power, that is the rating, okay. And this run, depending on where you are storing, it can run for several hours, okay. So, we are talking about thousands of megawatts, thousands of megawatt hours, okay, several thousand megawatt hours. That is a lot of energy, right. So, pumped hydro actually is the most common and the most popular type of mechanical energy storage across the world, okay. All right. So, we talked about losses, which are we talked about pump and motor losses, pump losses, and so on. So, let us talk about other losses in a pumped hydro system, losses in a PH storage system. All right. So, the first one are the motor and pump losses, and the second one we already goes hand in hand, turbine and generator losses, okay. Now, these are definitely the most intuitive and we know that. What else? There can be flow losses, because remember it is flowing through some channels. It is, I mean, the way I showed the schematic were two lines, but if you actually see here in this picture, actually there are some I mean there are these flow channels that go up, and then this may be even underground also, or okay. So, therefore, the flow paths, there can be some seepage, all right. So, flow losses, I would say, let us say through seepage, clear. There can be seepage into the ground, especially from the top reservoir, clear. From the top reservoir there can be seepage into the ground, because that is after it is pumped up, it is staying there. So, something can seep in, and there can be evaporation also during storage. Okay. And so on. So, these are some of the sources of losses, and we need to keep this in mind, and therefore, the efficiencies are never going to be 100%, but these are typically pretty high. I am talking about, when I say high, I am talking about 75-80%. 80% probably is a good ballpark number for most pumped hydro storage plants, clear. So, this is a very popular, probably the most popular type of mechanical energy storage that we have, okay. So, let us look at some of these, okay. This schematic, as you can see, is what I am trying to show. This is during the night time. So, what is generated from the power plant, only part of it goes to the consumer, and the rest of it is used for pumping the water up, and during daytime, of course, the entire supply from the power plant goes to the customer, plus whatever is recovered from the stored energy also goes to the customer, because this is when the peak load is, and the peak load, the demand is higher than the supply, all right. So, these are some pros and cons, we have already discussed some of them. So, this is a mature and reliable technology, there are hundreds of plants around the world, okay. If you look at globally, if you just search on Google, you will see there are lots of installations across the world. So, this is definitely very popular. So, USA has almost 19.5 gigawatts of capacity, that is a lot. 2.5% of base load is a lot, okay. The high overall efficiency 70 to 80%, it is quite fast, because this is hydro, okay. And you can also you can control the valve depending on the demand, you can control the amount of flow rate that you want to release, right, clear. All right. What are the disadvantages? The potential sites are limited, I mean, because you need a high altitude area. So, you need a high altitude reservoir, so you can only have it where you have hills, okay. And so, you cannot just, for example, in the West Bengal plain, in the Gangetic plain, I cannot have a pumped hydro storage plant, right. Environmental and political factors are also there, because just anyway, I mean just installation of a power plant, if you have to dig a reservoir, there are also this has some environmental impact. So, these also have to be kept in mind. Okay. So, these are some pumped hydro installations across the world, and you see how the popularity has grown from around 1911, in the decade of 1911 to 1920 there was none. Okay, probably there was one, I do not know, but after that it has slowly crept up, and and around the 1950s, around 60s and 70s it is very high. Then slowly it is coming down, because now I mean there are only a limited, as I said, there are limited number of sites where you can install them. Okay. So, therefore, the naturally whatever was available was probably exhausted by here. So, it saw a dip, and again it is expected to rise, because slowly, especially now in the later half, after in this new century, what we have seen is we have become more and more conscious about the reduced availability of fossil fuel. So, therefore, we have become more conscious, we have become extra conscious about energy storage, about having more efficient and newer plants, about having new and renewable energy sources, and so on. So, as a result, there is again a renewed vigor on such energy storage, and the focus has again shifted back to energy conservation, to energy storage, and therefore, several plants are due for completion in this decade. Okay. So, this is a projected figure. We may not be hitting this 60 mark over here, but we will have several I mean a significant number of new installations in this decade that we are in. Okay. If we talk about PHS installations in India, again of course, it is not like in the gigawatts range yet, but if you look at it in megawatts, it is not bad. So, the first one was in Andhra Pradesh, it was in Nagarjuna Sagar in Andhra Pradesh, and the capacity was 700 megawatts, quite a lot, and this was done in the 1980 to 84. Okay. Also, you will see that in India, of course, recently there has been a change, but there has been this planning commissions every 5 years, and that is when most of these installations are sanctioned. So, all these installations, if you look at it, look at the periods, they coincide with some planning commissions, right. So, next one, as we seen, that the next one was Paithan in 1984, and as you keep growing, this is, you can see that all these installations have happened. Okay. In West Bengal, there is one which is a pretty high power, which is 900 megawatts. It is in Purulia, and it was completed in 2008. All right. So, we also have it here, but otherwise what you will see is there is a bigger concentration in southern and western India. Okay. However, that being said, the one that is right now, it is expected, the one that is under construction is expected to be completed next year, is in Tehri Dam in Uttarakhand. The pumped hydro storage installation is in progress. The hydroelectric plant is already there, and there it is going to be, the installation is going to be 1000 megawatts, which is very high. Okay. So, overall, I see in India also this is quite popular. There are 11 installed plants already, and there is a 12th one that is coming up, and there will be maybe a few more over the next few years. Okay. So, pumped hydro systems is quite is very popular, and a viable and proven reliable mature technology. So, I am going to end this lecture by showing you a few pictures of pumped hydro installations across the world. This is in San Luis, California, and here you can see that the two reservoirs you can directly see, and this is where you are generating the you are getting the, you are pumping the water up and gathering the potential energy, which we are harnessing later. All right. Next one is in Scotland, Cruachan Reservoir and Loch in Scottish is actually lake, and as you can, it was established in 1965. It can store 10 million cubic meters of water at an operating head of 370 meters. Okay. So, almost 1000 feet or even more than that. Capacity is 440 megawatts for 1 hour. The annual generation is 705 gigawatts hour. This is again, it varies from, annual generation will vary from 1 year to another. In 2009 it was 705. So, and the third one is in Germany, in I even do not know if I can pronounce it correctly, Koepchenwerk in Germany, on the Ruhr River, and here also you see the two reservoirs, very nice. This is the lower reservoir, this is the reservoir at the higher altitude. Okay. So, that kind of brings us to the end of our discussion on pumped hydro storage, and this is, as I said, it is a very popular and mature reliable technology for energy storage, a mechanical energy storage, where water or hydro or whatever what energy is stored in the as potential energy and released later for generation during peak hours. Okay. So, with that, what we will do now is we will move on to the next form of mechanical energy storage, which is known as compressed air energy storage. Okay. So, compressed air energy storage, or CAES. What do I mean by this? So, as the name suggests, over here, look, in pumped hydro the energy was stored in the form of potential energy. In compressed air energy storage, the energy stored is in the form of pressure energy, okay, in the form of pressure. So, what is it? So, let us look at compressed air energy storage, or maybe I should first just give you a background of, probably all of you know, but it does not harm to just recap something for gas turbines. So, in gas turbine, what happens in the gas turbine cycle, and you would have studied in this course itself, the first thing that we have is a compressor into which air is pumped, or whatever, air enters and it is compressed, and when it comes out it comes out at a higher pressure, and because of the compression the temperature also is higher, has to be, right. So, then what happens is the next one that it goes in a gas turbine cycle is the combustion chamber, where liquid fuel comes in and the air and fuel is combusted, and what leaves is the combustion gases at high pressure and temperature. The temperature even further rises and it comes out in this form, and which is next fed into a turbine. Right, and this turbine rotates as a result and it generates electricity. It is connected to a generator and it generates electricity, and what comes over here are the exhaust gases, which is at a sufficiently high temperature still. So, this is air, this gets compressed and so on. Clear? Now, in energy storage plant, what happens is it is something similar. What happens is, in the sense that we still have a compressor which is used to compress air. Okay. So, let us draw that again. So, this is, I would say, this was a gas turbine cycle. Okay. So, in a gas turbine, in an aviation engine, for example, in the aircraft engines, this exhaust gas is let go in the to the atmosphere, and that creates the thrust, as a result of which the airplane moves. However, in the industrial turbines used in power plants, especially if you are talking about combined cycle, these exhaust gases actually form the source of heat for the bottoming cycle, which you have studied before, and that bottoming cycle can be a steam turbine Rankine cycle, or if you are talking about even lower temperature, it can be an organic Rankine cycle, it can be a Kalina cycle, and so on. All right. So, in compressed air energy storage, what happens is you have a compressor. And here the air comes in, sorry, over here, and it is compressed and comes out in the compressed manner. But next what happens is, then this one is not fed to a combustion chamber like in gas turbine. Instead, what happens is, I am going to draw something and then explain to you. Let us say this is my ground. So, what happens is, this compressed air comes in and is stored in a large reservoir. Let me draw that over here. It is stored in a large volume, an empty volume, where this compressed air goes and is stored. Okay. Next what happens is, so what is this air at? This air is going to be, because it has been compressed, its volume is low, lesser than what at least it was over here, and it is at a higher temperature. Okay. Later on, ideally what will happen is, this compressed air is going to be released and when it is released, where will it go? It is going to go to a turbine which will be rotated. It is a gas turbine, more specifically air turbine, and we will use it to generate electricity. So, this is air in, this is exhaust air, all right, and as before, this is where I am going to generate the electricity, all right. And let us draw a few more other appendages. I am going to have a motor generator set, and which is going to have a shaft which is going to connect these two. Clear? So, this is how a compressed air energy storage works. Again, to repeat, what happens is, you take air and you compress it in a compressor, so that it is now at high pressure, therefore low volume and at high temperature, which is now stored in a reservoir. So, let me name that as R and say that R is reservoir, C prime is compressor, T is turbine, M is motor, G is generator. So, all this good stuff, all right. Now, typically what happens is, however, there is a little variation to this. No, there are several variations to this, but even in the regular case, what happens is, the air that comes after compression is at a high temperature. Now, if you put it in a reservoir, what will happen? Okay. Or rather, okay, before that, if you put it in a reservoir, that it will lose heat definitely, but if I can bring down the temperature at the high pressure itself, then what happens? The volume of the compressed air is going to shrink even further, all right. So, again I repeat, what I am trying to say is, the compressed air that is coming out of the compressor is already has been compressed. So, it is at it occupies lesser volume, but it is at a high temperature. If I can cool down while keeping the pressure the same, then what will happen? My volume will be even lower, because I have brought down the temperature. So, the volume required to store that air will be even lesser, or in other words, for a given volume of reservoir, I can store more mass of air, either way, whichever way you look at it, all right. However, when it comes out of the reservoir and goes to the turbine, I would like it to be at a high temperature, because if the turbine inlet temperature is low, the amount of work that I am going to get out of it is also going to be lower. So what do we do? So the way it is done is, I have a heat exchanger here. So I will have a heat exchanger over here. So what kind of heat exchanger is the next question. Okay. So before that, so if there is a heat exchanger, what happens? This fluid, the compressed air coming out of the compressor is going to lose heat, and the air that is going to the turbine is going to gain that heat. But here there is a problem. The problem is, these two are not happening at the same time, these two are not flowing at the same time, right. The compressed air is getting into the reservoir during off peak hours when I am storing energy, whereas the flow to the turbine from the reservoir is happening during peak hours. They are not at the same time. Actually, that is the whole principle of energy storage. You store it at some time for a certain interval of time so that you can use it later. So then what do we do? Okay. So I think the answer you already know, because you have studied from P.K. Das's lecture, from Professor Das's lecture, you have studied heat exchangers and the two types, recuperator and regenerator. So therefore, I cannot use a recuperator in such a situation. I have to use a regenerative heat exchanger. Okay. So therefore, a regenerative heat exchanger. So what is that regenerative heat exchanger? It can be like a pebble bed. Okay. So let me write that here. Pebble bed regenerative heat exchanger. So what is this? This is a volume consisting of some pebbles or stones. So these are materials that have high density and high specific heat. Typically that is for thermal energy storage, that is how we do. So what happens is, when the heated air from the compressor is flowing through it, it will lose heat to these pebbles, which is going to store it. And so what comes into here, what comes in to the reservoir is high pressure, low temperature. And similarly, when it is released, it is made to flow through the same reservoir, or through the same regenerative heat exchanger, sorry, where it picks up the heat from these pebbles. These pebbles are good candidates for energy storage, right. So it picks up the heat from these pebbles and goes through. Okay. Pebbles is just one example, we will see more examples later. We will list down other types of heat exchangers that can be used for this purpose. So overall it is clear. Is it clear how it works? Okay. So I will just summarize it over the next 1 minute, and before we end this lecture, I have air coming in, let us say at room temperature, low pressure, compressed to high temperature, high pressure, and then and so therefore its volume is low. It is further cooled down by passing it through a regenerative heat exchanger, where it loses heat to, let us say, a packed bed of pebbles, and then therefore what comes out of the heat exchanger is air at high pressure but low temperature, and then it is stored in this reservoir R. Okay. Then what happens? During the peak hours, the same air goes out and is made to flow through the regenerative heat exchanger, where it picks up the heat from that packed bed of pebbles. So now it is still at high pressure, high temperature, and then it enters the turbine, gas turbine, where it makes the gas turbine rotate, it generates electricity and exhaust air at definitely lower temperature and lower pressure than the inlet comes out. Clear? All right. So this is the compressor mode during off peak hours, this is the turbine mode during peak hours. So the extra energy that I have, because my demand is low during off peak hours, is used to run this motor generator set, especially the motor which runs the compressor, and during peak hours the what I get from this turbine is in addition to what my power plant is generating. Okay. So, this in a nutshell is compressed air energy storage. So, in the next lecture what we will do is, again like before, we are going to do a bit of analysis on this. How do we solve for problems, or how do we calculate the performance, the volume, the pressure, etc., for a compressed air energy storage, and then we will look at some examples of installations across the world. All right. So, thank you very much, and we will continue on this topic in the next lecture.